Okay, so we've been talking about rate laws, and what rate laws tell us is how the concentration of our reaction changes over time, depending on which component we're looking at. And what we really want to know when we run a reaction is how much of everything is present in the reaction. How much starting material is there at after 2 minutes? How much product is there after 3 minutes, right? And when can we stop the reaction and say that we have this much product in our reaction and this much starting material? And all of that. And rate laws are great for, they kind of tell us what the concentration is at each point. But what we really want is we want kind of a formula that we can plug in a certain amount of time and tell us what is the concentration at that time, right? Because right now, the only way that we have time kind of related to this is if we draw the curve, find the tangent line, figure out the rate, all this other kind of stuff, right? And that we have to do experimentally. We have to kind of measure it. But what we want to be able to do is take that K value, that rate constant, and a certain time, and use that to predict how much of our material is going to be present in there. And so to do that, we look at integrated rate laws. So we're going to relate concentration and time now. Concentration and time. And we're going to do that through integrated rate laws. And so we're going to have three different versions of this integrated rate law, and they're going to depend on the order of the reaction. So let's start with a first order reaction, because that is the one that we'll probably use the most often. So if we have a rate law that says the rate equals our rate constant times the concentration of A, right? This is the first order rate law. We can also say that this is the change in the concentration of A over the change in time, right? And that's just kind of restating what we stated in the previous videos, all that good stuff. So I'm going to go one step further and say that this is our initial concentration minus whatever the current concentration is, all over the change in time. So I'm just kind of expanding delta A, delta the concentration of A to be the initial concentration. That's this value here. So that's how much of A we started with. And then all of this. And what we can do with this, so this value, whenever we have a delta t in there, we can use calculus to kind of make this into, if we know that this changes over time, we can use calculus to show, give us a formula that actually, if we plug in t, will tell us what all these values are. And so we're not going to do the calculus, but if you do an integration of this formula, delta A, or the concentration of the initial concentration of A minus the current concentration of A all over delta T. If you integrate that, what you get is that the natural log of the concentration of A equals negative KT plus the natural log of the initial concentration of A. This formula is really useful, right? So this is the integrated first order rate law. So any first order rate law, any first order reaction, right, will follow this formula. And what's nice is that a lot of these are known things, right? We know the rate constant, or we can look up the rate constant for a reaction, right? Or we can experimentally determine it. We know the initial concentration because that's how much of A we put into the reaction to start it. And so we have two known things, and then we have two variables, right? We have time, T, and we have the current concentration of A, right? So these two things are related. So what this integrated rate law is telling us is that at time T, the concentration of A, which is of course square brackets with an A inside of it, depends on the initial concentration, right, which is A0, whoops, and the rate constant. So really this kind of makes sense, right? What this is saying is that the amount of material that you have at any certain time is dependent on how much you started with and how fast it's disappearing, right? That makes total sense, right? And so what we've done is we put a mathematical expression on that, right? So if we find the rate constant and we know our initial concentration, if we know the order of the reaction, we can figure out the how much concentration there is at any point in that reaction. Okay? So the first order rate law is this one. The natural log of the concentration of A equals negative kT plus the natural log of the initial concentration of A. So definitely write that one down. That's one we're going to use a whole bunch. All right. What if we go second order? So let's do a second order rate law. Second order integrated rate law. Rate equals K times concentration of B squared. Right? So this is a second order reaction. We're not going to do, well, this is the type of second order reaction we're going to focus on. We're not going to do one where we have two different concentrations in our rate law. So concentration of K times, or K times concentration of A times concentration of B. We're not going to do a rate law for that one because it gets super complicated. We're going to do the same thing. We're going to expand this out. We're going to do calculus to figure out what everything is. And what we're going to get is 1 over the concentration of B equals KT plus 1 over the initial concentration of B. So again, we have the same knowns, we have the same unknowns. Once again, the amount of B that's present at the end of our reaction, or at any time in our reaction, is dependent on how much we started with and how fast it's disappearing. Okay? So again, that's great. We have another expression, and these two expressions I hope you're noticing are kind of looking the same. All right, now let's do a zero order integrated rate law. These are this one is pretty, right? So what's a zero order rate law? That's if the rate equals K. And so concentration of A equals negative KT plus the initial concentration. So in this case, you basically just have your material is disappearing at rate K, and it doesn't matter what the current concentration of A is. This is just a nice linear expression, right? So you're always going to have whatever your starting material is minus however has much has disappeared. So zero order rate laws are really easy. All right, so let's put all of these next to each other. Okay, so here's our first order rate law. Here's our second order rate law. And here's our zero order rate law. Right, so this is zero, first order, and second order. And what you notice about all of these equations is that there's a lot of similarities between these equations. I shouldn't say they're basically the same because they're not. There's a lot of similarities. And notice that all of these equations are linear equations. Right? So if we go back to algebra, the format of any linear equation is y equals mx plus b, right? In this case, our m is our slope, right? So this is the slope. And so if we graph these integrated rate laws, the slope of each one of these lines, depending on if it's a zero order, first order, second order, the slope of those lines is going to be k, or in some cases, negative k. Right? And so if we graph these out, so this is another way that we can kind of find a value for K. If we collect the data and know the concentration and the time that we measured that concentration at, we can do a graph of it, fit it to one of these equations, first order, second order, or zero order, whichever one gives us a straight line, and the slope of that line will be k, or it'll be negative k, right? And then you have b, which is, of course, your y-intercept in most in linear equations, and the y-intercept is the one that's related to your a0. Depending on which order you have, they're going to have different things. So there's a worksheet that allows you to kind of play with this and work out what are the parts of this, use these formulas, plug stuff in and all of that. Um, Sometimes there have been questions in the past about kind of using natural logs and how do we use natural logs. So if I have time, and it might not be right at the beginning of the week, but I will do an example or two of integrated rate laws and how to kind of manipulate natural logs just so that people see it and remember how this goes. Um, but really, a lot of this is going to be find the initial concentration, plug that in. Find a K value, plug that in. Or if you're given a time and a concentration, right, you can plug in concentration time and find your K value that way too, right? So if you know your time, you know your concentration, and you know the order of the reaction, then you can plug that into any one of these equations and you can find out what the rate constant is. So again, there's four pieces of information. Concentration at time t, time, rate constant, and initial concentration. So those four things, K, T, concentration of A, and concentration of A0, right? Those four things, I can take away any one of those and ask you to solve for that one, given the other pieces of information. So practice that, be familiar with how to do the algebra to get those values in there, and that'll be a great place to start. All right, so the next one we're gonna talk about is half-life. We figure out half-life from the integrated rate laws. That should be a nice short video and hopefully pretty straightforward. So I'll see you in that one.